Okay, so here, let me draw a view of how the motors will be stacked, looking up at it. Okay, so let's just say here's the bicep bone, and the bicep bone's going away from us to the shoulder, right? There we go. Each of these motors is coming like this. Right? Gets smaller as it goes away from us. And then they're just going to continue to be stacked. Like that. Getting smaller as they go away from us. And then we get to stack above that a whole new row. Like that. Above it. So it could be stacked 2 or 3 tall. I can draw it more clear here because we got overlapping lines. It's hard to see what's going on. Right? So they're stacked tall, height-wise. So we got clear air channels going through the center of each column. And the columns can be stacked 2 or 3 high, like that. And what will be great is in order to separate the columns, we can create a crossbar between columns. The cross beams will strengthen it so they don't lean left or right. So that drawing got so convoluted when I started adding all the details. So let me just draw a simpler version. Alright, so we got one row, or one column. Here's the next column. Right? And in order for, well, let's draw a third column. Alright. In order for them not to lean left or right, because they're going to be strapped down tight with string, sewing them into the bone, right? And sewing them into one another. But they won't have a lot of strength side to side, so we're going to add, and we got to keep them separated. They can't be touching. So we're going to add little crossbars like that. Just like a little metal nail, which we can wrap in cloth and tape and then sew into the various motors. And that won't prevent too much airflow either, because it's just going to be a single little metal nail. The little dark lines horizontal I drew are just going to prevent the motors from tipping over left or right. And the air will be able to flow nicely right through the middle of these columns of motors, like that, with very little obstruction. What's up, Ben Cost? So that's my design for how I'm going to strap down the motors onto the bone. So those little cross beams are critical in order to maintain their vertical positions. And what's great is, so let's say this is part of the bicep, right? The bicep's coming like this, like that. And the robot falls and a crushing blow gets put down on the bicep, like if somebody punched him in the bicep. Well, that blow will be hitting the tops of the motors, and all the like the output shafts, the little pulleys on the ends, those won't get affected it's actually going to hit the bodies of the motors, the DC motors. And so the force will go into the top of this body and then transfer down into the next body, into the next body, all the way down to the bones. And the only thing that would eventually crush would be perhaps, let me just draw what the crush would look like. So the top motor, let's say, is like this. It would crush down like that, maybe. Or maybe this would crush. So that the actual motor itself would get actually crushed. But I think that would be pretty difficult because it's a metal DC motor. That'd have to be a lot of force. So most likely, unless if like a sharp thing kind of crashed down right in the center, if the force hit right here, it would be very difficult to crush a metal plate right here. That'd take a lot because it's round. It's hard to crush the arch. That's why arches are used for bridges. They're very strong in nature. A curved shape is very strong. Even the top surface of this is curved. So that's actually very strong. It's a strong shape. So these cylindrical motors will be hard to crush. So that will form the strength of my robot in terms of not breaking when it falls or collides with something. The motors themselves, stacked on each other in vertical columns, are going to be the only thing preventing the robot from breaking. Plus, they might be able to shear away some of that force. So if the force was like this, the whole column might kind of, have some give to it. It might bend a little bit, and so that will mean it's even less likely to break, since the motors could just kind of shift around in position in order to accommodate that tough force that just banged into them. Because they're mounted, in vertical columns going lengthwise with the bone. And if it got pounded by a rock being thrown at it like that, they could all just shift that way. They'd all just kind of bend. The whole column would just kind of like lean, like pushing the top of a skyscraper. The whole skyscraper would just lean a little bit. So it would be very difficult to break this. And obviously the bones are difficult to break because they're all created with round structures. They're round. And they're hollow and they're very flexible, made of fiberglass, so that they're able to bend, substantially before they break. And the ligaments themselves are balls and cups, so that's hard to break because that's all round surfaces, no weak hinges or anything like that. And they could even, get slightly stretched out, just like when you sprain your ankle, the ligaments stretch out a little bit. But because the ligaments of my robot will be elastic, even if they did get stretched out from a sudden jarring, twisting of its knee, there's a good chance it could snap back without any real damage to the ligaments. Because the ligaments are made of spandex. They're able to stretch and then reassume their original shape. So I think the robot will be very resilient to damage with this design. So that's another advantage of the design. If I were to have used the vertical motor shaft design like this, where the motor shafts are coming out vertically from the bone, that would be very easy to break. If you were to put pressure down like that, it could bend this little weak shaft. But because I'm laying the motors parallel with the bone, running with the bone, then any forces won't be able to break the motor output shafts. Instead, it's going to be just putting all of its pressure onto the metal body of the DC motor itself, which is the strongest part of the motor. That's where, if you had to pick a place on a motor, the last thing you want is any pressure on the pulley. That thing's going to bend easily. But putting pressure here, that's the strongest part, so that's good to go. So this is a very strong way to do it.